Welcome to Networks Professionals.
Welcome to this explainer. Right beneath the surface of the websites and apps we use every single day, there is this massive, silent logistical operation going on. It literally never sleeps. We're talking about a sprawling global infrastructure that connects billions of devices across oceans and continents in just a matter of milliseconds. It's the invisible force that keeps our modern world communicating, and it's happening entirely behind the scenes. But have you ever stopped to wonder how exactly a single piece of data, like a buffering video or a message to a friend, actually finds its way through billions of devices without getting completely lost? Well, at this massive internet scale level, data doesn't just wander around hoping to bump into its destination. There's a deeply structured, highly intelligent routing architecture that is constantly calculating and recalculating the absolute best paths across the globe. Okay, let's dive into this. The engine driving all of this is called BGP, which stands for Border Gateway Protocol. Basically, you can think of BGP as the internet's ultimate global mail sorter. It acts like this gigantic digital postal service, exchanging routing and reachability information 24/7 to determine the absolute most efficient path for your data to travel. It's the underlying language that allows entirely different networks to actually talk to each other and negotiate exactly how traffic should flow. Moving right along to Section 1, the Internet's postal service. Now, to really grasp the sheer scale of this operation, we first have to understand how the Internet itself is divided up both geographically and administratively. See, the Internet isn't just one big uniform blob. It's actually chopped up into thousands of completely separate, distinct networks that we call autonomous systems, or ASs. Think of an autonomous system just like a major regional postal hub. Major internet service providers, massive cloud networks, big enterprises, they all operate as their own ASs. To give you an idea of the scale we're dealing with, there are over 70,000 active ASs routing traffic today. For example, Verizon operates as AS 701. So every single time you send data across the world, it's basically being handed off from one of these giant postal hubs to the next until it reaches its final destination. Let's move to Section 2, how BGP maps paths, and see how this builds out. Managing the complex handoff between all these massive hubs requires a very specific kind of map and a highly methodical set of rules. So BGP relies on something called path vector routing. What this means is that instead of just lazily counting the number of hops from one router to the next, BGP actually remembers the full path information. It keeps an exact step-by-step itinerary of the networks your data has to travel through, kind of like a super strict delivery truck manifest. By knowing the whole sequence, BGP prevents what we call routing loops. You definitely don't want your data just driving in circles forever. Plus, this strict itinerary ensures the traffic actually complies with specific routing policies. Now, to handle this absolute logistical nightmare, BGP actually operates on two entirely different fronts: internal BGP, or iBGP, and external BGP, or eBGP. Imagine iBGP as the busy dispatcher inside one single massive postal facility, making sure packages get from the loading dock to the exact right sorting bin. eBGP, on the other hand, is the dispatcher coordinating between entirely different global facilities. It's the one managing a shipment moving all the way from a hub in New York to a hub in Tokyo. BGP flawlessly handles both the inside coordination and the outside negotiation. And this brilliantly illustrates how serious BGP is about getting things right. To guarantee the reliable delivery of all these vital routing updates, BGP operates specifically as a Layer 7 protocol, and it runs entirely over TCP on port 179. It absolutely does not leave massive infrastructure updates to chance. Because it uses TCP, it ensures that every single digital handshake and every single route update is fully acknowledged and securely delivered between the routers. Moving to Section 3, the Essential Network Navigator. So why does all this underlying technical routing architecture actually matter to the businesses running the world? Well, it matters because BGP is the Internet's indispensable navigator. Without it, the Internet literally wouldn't know how to transfer a single byte of data globally. But it's way more than just a basic map. BGP provides absolutely crucial redundancy. It's constantly analyzing paths to route your data around downed lines and fiber cuts, making sure the network stays highly available even when disasters strike. It also balances heavy network loads so that no single hub gets overwhelmed. And maybe most importantly for the corporations running these hubs, BGP lets administrators enforce incredibly specific, policy-based routing. This means a network can dictate exactly which paths traffic should or shouldn't take based on complex administrative rules or commercial agreements. It's highly intelligent, business-driven routing.
Now for Section 4, security and BGP hijacks. And folks, here is where the story of the internet takes a bit of a dramatic, actually kind of unsettling turn. Because for all its power and intelligence, this global infrastructure has a profound fragility built right into its foundation.
Now, what's really interesting about this slide is the sheer vulnerability of it all. Believe it or not, BGP operates largely on a system of mutual trust. It sounds crazy, but the entire global internet, our banking systems, government communications, critical infrastructure, it all relies heavily on an honor system. When one major autonomous system announces to the world, hey, I know the fastest way to get to this destination, the other systems generally just take their word for it and believe them. And unfortunately, that blind trust leads to what we call BGP hijacks. BGP was designed way back in an era where network operators literally knew and trusted each other. So today, malicious actors, or honestly, sometimes just clumsy engineers making accidental misconfigurations, can cause massive network outages. It's basically as if a rogue postal hub suddenly claimed it owned the route to every single mailbox in Europe. Instantly, all the traffic meant for those real destinations gets sucked into the wrong network, causing these massive global traffic leaks. There was actually a super famous example of this back in 2008, where a simple misconfiguration in Pakistan accidentally knocked YouTube offline for the entire globe.
So, the crucial point is that the internet community is actively fighting back. They are adopting cryptographic security protocols to fix this. And the cryptographic hero of our story is RPKI, which stands for Resource Public Key Infrastructure. By rolling out RPKI, networks can finally validate network destinations and validate the actual routing paths. Organizations don't have to just blindly trust these route announcements anymore. They can mathematically prove that a hub actually has the authority to claim a specific route. It's a real game changer.
But it still leaves us with a really vital question to think about. When you hit send on your most sensitive data, is it actually taking the safest path across the globe, or is it just blindly trusting a rogue announcement? While advanced tools like route origin authorization, or ROA, and local preference calculations are out there for those who want to dive deeper and close these gaps, the reality is the internet's core still beats on a surprisingly fragile honor system. Until RPKI is universally adopted, who is really routing your?
Thanks for watching.